recording, and it was not garbage day this morning, which means it's Thursday. So welcome back. Our second to last Thursday together, as it turns out. So I have the webpage open to make a couple of announcements. I will be working on grading homework 5. I'll let you know when it's ready. It's going to take a minute. Formative example 5. Nope, that's not even a thing. Oh yeah, that's where we're at. Hang on, let me reload with some more caffeine and see if I can find some words. Formative assessment number 5, that's the thing. That is going to be due on Monday. And then I believe I sent out an email this morning about homework 6 being available. So you're going to be using the examples 7A and 7C. So CFA invariance and IFA invariance in that one. And it is worth 20 points, 18 of which are computational. So you get all your green boxes and you will know where you stand. And then you can decide if you want to revise homework 5, and if so, that's due at the end of finals week as well. And I think that's it. Did I talk about office hours last time, or was that the other class? I think you did? Okay, yeah, office hours every day that I would normally be teaching are office houring. So you can find me 4 days a week during finals week if you need help with anything of that. And the TAs are also available, at least this week. I haven't asked them about finals week, but they've been through the homework and are ready to help you with that as well. Yeah, so any questions or things I'm forgetting about that? Nope, okay, cool. Then we were in lecture 8 last time talking about higher order factor models and broken items and stuff like that, and how to fix broken items. So I wanted to pick up on slide 18 and talk about method factors and specific factors as a way to capture unintended multidimensionality. So that's where we'll be. Lecture 8, slide 18. So if you're in the position where you're analyzing data that are already collected, you can't fix the items, you can't make them better, then you have 3 choices for how you would introduce additional relationships among your items that you did not foresee and that you do not think represent real traits. The obvious one is an error covariance. So it allows the items to have something in common that is above and beyond what they already have in common due to the latent factor that they are indicators of. And this is kind of a throwaway thing, like, oh, let's just put an error covariance in, it's fine. I would not add them unless you can be prepared to defend them and expect them to replicate. I would also say this is, do I have a slide on that? Yeah, I don't know if I do it or not. Error covariances are not always a choice. As a general guiding principle, error covariances are possible whenever your model is trying to recreate some kind of correlation matrix, whenever there is an answer key to come back to. So that would mean standard CFA when you're trying to recreate a traditional Pearson correlation matrix. That would be IFA when you're trying to recreate a tetrachoric or polychoric matrix. Then you can have error covariances. Any kind of full information maximum likelihood that involves link functions, so categorical outcomes, there's no such thing as error covariances in those models. So you don't have that as an option in that case. You can also have separate latent factors that are both method and trait specific. So by method meaning something else about the item than what you had intended, such as how it's worded. So in example 4, we had looked at the trait of situational forgiveness, in which 3 of the items were positively worded, 3 were negatively worded, and we ended up with 2 factors with that distinction, and the model fit pretty well. The 2 factors were only correlated about 0.6, indicating that forgiveness and not unforgiveness are not the same thing. That is generally dissatisfying to folks, though, and they usually want to try to do something else. And so the alternative goes by a lot of different names. In the IRT world, it's called a bifactor model. In the CFA world, they're called method factors, and they're sometimes called specific factors as well. And the idea is that you're introducing a latent factor that would capture the additional correlation among items due to whatever reason you think that it is. So I have a couple examples I want to show you of how that would work and what kind of constraints, more importantly, you would want to put on there to ensure the interpretation of your factors is what you want it to be. So error covariances are only possible when there is a saturated model. Yeah, I knew I had that in there somewhere. I just remember where. So when there's a covariance matrix to come back to, all of CFA only when using limited information estimation for IRT. Otherwise, you need a method factor, and that is why bifactor models are such a thing in the IRT literature, is because they don't have a choice to do it any other way. So it's like they're stuck with it. So to do a method factor to represent a correlation between two errors, two pairs of items, two items, I should say, you would fix both of their loadings to 1. If it's expected to be a positive error covariance, if it's a negative error covariance, you need to fix one of them to -1, and then you would estimate the factor variance. And that won't be the same value as an error covariance, but it does the same thing. It builds in another reason why those two items would be related. So theoretically, then after whatever's left over after that is unrelated. There are equivalent ways to do this, but I know we talked about this before, but I'm bringing it back because now we're going to expand on that. It's like, do you want to try to explore why you have this extra correlation, or do you want it to go away? So if you want to explore it, then you might fit a separate factor for the two items that wanted to be related. So in this example, this is from lecture 4. There were 6 items altogether that were thought to indicate some kind of social interaction anxiety. 2 of them had to do with public speaking specifically, and so this is one alternative. This approach would be useful if, instead of just wanting the additional relationship that has to do with public speaking to go away, you want to actually explore individual differences in it. I would do it this way, because then you have a trait that contains that whatever information these 2 items are providing. It is a separate trait from the other 4, though. And so they're not contributing to what was called social interaction anxiety anymore. They're their own thing. Now, however, what do you think would be the consequences of reliability for this? Do you think it's a good idea to have 2 items on one trait? No, probably not. Let me put it this way. If you were taking like a licensure exam to determine the rest of your career, would you want it to be only 2 items? I would not. No, I feel much more comfortable with like 300 items, because then I can miss a bunch and it'll be okay. Not so high stakes. That's why you're also answering like 300 homework questions this semester, because you can miss any one and it won't kill your grade, right? You don't want to know how many questions you've answered. I know how many you have. I'm not going to tell you. But you can feel proud about that by the end. If you just want the extra relationship to go away, that's when you would do an error covariance if it's a CFA type model, or a method factor. So the distinction between the picture on the left and the picture on the right is that the last 2 items can still contribute to the general factor on this version of it, and then there's an extra factor beyond that. So it's a 2-factor model, but it's considered a method factor model or a bifactor model because of that. Software wants to update. That's how I know it's Thursday. There we go. Go away. And so I had to add to the person's diagram here that I stole this from in your textbook the word extra, because this is not just public speaking anxiety. It's whatever public speaking is beyond social interaction anxiety, right? These 2 items have 2 different sets of loadings going to them. So the interpretation is not the same in these 2 models. And in some cases this makes sense, and in other cases this doesn't make sense. So for instance, let's say that you are examining latent ability in mathematics, and you have different kinds of items. So like my son in 3rd grade would have addition items, subtraction items. He calls them plussing and minusing, of course, timesing and dividing. That one doesn't have a special name. So I could have a test that's composed of all of those skills and have a general factor of mathematics that it's supposed to measure. But odds are good the items that address some skills in common, like addition specifically, will have an extra relationship. So you might be tempted then to say, well, let's just do an extra addition special factor like this. But how do you think about what addition is that is orthogonal to math? Right? Because that's what this is saying. They're saying that whatever this extra factor is, it's unrelated to the main factor. It's above and beyond. And I don't know how to think about that. Like, how do you have an extra trait of addition that is not math? So in that context, I think it's a little weird, and I wouldn't buy it. So the 2-factor model shown on the left has a correlation between these 2 because it's thinking of them as 2 separate traits, each identified by separate items. This one has all the items loading on the first trait and then just an extra specific factor, as it's called, for that. So I had recommended this type of strategy, the one on the right here, to several of you that ended up with a bunch of error covariances where it was like the same combinations of items. That way you can have a factor that maybe captures what they have in common as opposed to multiple separate error covariances, and that may be more parsimonious in some cases. So, does this make sense so far? Questions?
Yeah, I have some questions.
Okay.
So, in terms of model identification, if you end up with 3 factors, how do you decide, like, do you have to go with method factor, or it's not gonna be like over-identified to be able to test it? Like how, or do you have to like have 4 factors? Does that make sense?
Can you make a more specific example?
Yeah, so I have bonding social capital
Okay.
and bridging social capital.
Okay.
And then there's this thing, trust,
Okay.
which is sometimes considered social capital and sometimes not, and it's kind of up in the air.
Okay.
So if I do the 2-factor model, but with the 3 factors and the error covariances, then I can't test it, right?
You can't test what?
Like I can't, the model is just identified at the structural level, right?
If you just have if you have correlations among the 3, yes, you can't test a higher order factor unless you put some sort of constraints on the structural model that would reduce it to fewer degrees of freedom.
Okay.
So all of these are identical in terms of how they would fit. That's the thing. This is like, it's a choice as to what you want to do with your factors downstream in your structural equation model, which is where we're headed. It's like, do you want to make this a thing? Like public speaking anxiety as a new trait that's indicated by these things to predict something else or be predicted by something else? Or do you just want it to like control for it and make it go away? Because the right picture is the control for it, make it go away kind, because these 2 items are already contributing to the main factor that you care about. So I think my answer to you would be like, do you care about trust, or are you trying to make it go away? And you'd have to decide that. I think these kinds of specific factors would be useful for, like, you had pairs of items that were like the same, like sports or kids or something. Like those would be the go away kind, I think. You would address the additional correlation that way. Question from the Zoomers. So you can get away with 2 items on the specific factor? Yes. You can if, so check out the picture. And what is my caveat? This is the finger caveat today. You can have 2 items on the specific factor and have it be identified if you do what? The answer is in front of you. Include the covariance between the factors? Yes. And if constraining, not thresholds, right idea though? The things with the 1s on them? Loadings, yeah. So if you have 2 items on a factor and the factor is uncorrelated with anything else, the way to make it identified is to constrain the loadings to be equal to each other. Then it's okay because you're estimating 1 loading for the 1 covariance between the items. Otherwise, you would need to have a correlation between the factors that's different than 0 to make this identified, and then you could estimate a separate loading for the second item, so long as there is a correlation. If there's not one, then it's like it's by itself and it's no longer locally identified. That's a phrase I don't know if I've defined. Like locally identified means within a factor, or would you be able to solve it if it were all by itself? So this factor right here is not locally identified, but the model is still identified because of the covariance between the factors. I can't talk today. I think it's time to switch back to water. I'm going to move the Mountain Dew out of my reach and put the water bottle in front of me. I got to be my own friend. By the way, Jonathan wants me to say hi to everybody. He just arrived. He's on a field trip today, so hi to that. He probably wants to remind me that I promised to pitch his class to you, too. So he is teaching a Bayesian version of what he calls psychometric models, which is analogous to what I'm doing in a frequentist perspective. I'll tell him later, people are saying hello back. So for those of you who are interested in learning about how Bayes interfaces with the world of factor analysis and structural equation models, I would encourage you to check out that class in the fall. He is going to be using Stan and JAGS software, I believe. Anything else, Vladimir, that you remember from last time?
Stan.
Stan?
R.
Stan and
Yes.
R, or
Yes.
RStan or whatever?
RStan. Yes,
RStan.
That's the package. That's
Stanner.
what we use.
Yeah, and don't ever ask me for help with that, by the way. It's not gonna happen. So I will direct you to him for all things Bayesian and Stan-like, because I tried to learn it last summer and it did not go well. So there's some things in life I just decided I'm okay with not knowing. I'm fine with that. If I start learning new stuff, the stuff I already have is gonna fall out, so just gotta keep it all together. So yeah, Bayesian psychometric models, including this kind of stuff. So here's an example of a series of models that I think are useful and interesting. So this is a slightly older paper, but I like it anyway. There's 4 different models that the authors fit to the items from this scale. So this is a life orientation test. I have no idea what this is as a trait, but we'll just go with it. I'm guessing it's a very old questionnaire. They have 3 positively worded items and 4 negatively worded items with respect to this. And so they're fitting 4 different models, and I'll show you each of these in sequence. Single factor, which doesn't fit well, 2 factors due to wording, so a positive factor and a negative factor, a bifactor model, and then what they're calling is a random intercept model. And if you're like, wait, is that the same random intercept that I already know is a word? Yes, it is. Yes, it is the same thing, because latent factors are random effects, folks. They are. So what to do about the method facts? So here's some pictures from that paper. We have, we're calling it optimism as opposed to life orientation, which makes sense, I guess, because if you're going with the positive direction here, I expect the best, I look on the bright side of things. That sounds like optimism to me. So note in this case, they decided not to reverse code the items. So 4 of these items you would expect to have negative loadings if the trait were oriented towards positive. Here's the 2-factor model in which we split it up into optimism and pessimism. Here is the M+ code that would correspond to that. So opt is the name of the trait here. Variance fixed to 1, mean fixed to 0 for identification. All the loadings and intercepts and residual variances estimated. 2-factor version in which we add a covariance between the 2. And to the extent that this covariance, which is a correlation in this metric, is less than 1, that's evidence for a 2-factor model, which did fit better, as you might expect. And then, so here's the solution that we came up with. So for the 1-factor model, we have 3 items with positive loadings and 4 items with negative loadings, and they're all fairly strong. And quite frankly, I'm surprised this didn't blow up. Because when I've seen this kind of thing in practice, the factor doesn't know which way to go. Because it's an equivalent model if the first 3 were negative and the last 4 were positive, and then the factor would be called pessimism. And right now it's oriented towards optimism, but they're the same thing. And so this kind of thing, I do know in Bayesian versions of these models will cause problems because it doesn't know which way to go. So you'll see like a chain that'll like shoot up into like 2 different directions where all the loadings are positive and all the loadings are negative, and they're equivalent models in that case. So it can be a tricky problem if you're trying to avoid reverse coding like they did. Note that in the 2-factor model, all the loadings went positive. So you would expect a negative relationship between these 2 given the orientation of these items. And I have a note here, a higher order factor could be included if these 2 loadings were fixed to 1, but it would fit the same as just allowing the covariance. So it's the same thing as fixing the 2 loadings together or allowing a covariance, but not both. Then they tried a bifactor model. So this is your classic example of what a bifactor model is. You have what is known as a general factor, the thing that you care about, that every item loads on. So we're calling this general optimism. And then we have these specific factors, or method factors is a synonym for that, in which the positively worded items all load on this one, and the negatively worded items all load on that one. So it is 3 factors, but importantly, they're not correlated. If you try to correlate them, it will not be identified because everything is loading on everything at this point. In terms of like each item has 2 things that it's loading on. So the code for that would look like this. We have the general factor loading on every item loading on it. The specific factors, all of their variances are fixed to 1 for identification. Their means are fixed to 0 for identification. and then I shut off the covariances. So within M+, there are two ways to shut off covariances. The long way is to do it manually like this, where you say with at 0, and that removes the relationship. If you have a whole bunch of those and you don't want to type them out, then you can add an option under analysis that says model equals no covariances. And then that removes all the default covariances and you could just add the ones in that you want. Sometimes that's less typing. So that is an option instead of writing out all of these different things. Question, you're using the with code, so is this assuming WLSMV? It could be limited information estimation within an IFA model, or it could be full information estimation in a CFA model. Either of those would allow the with, and these are factor covariances, not error covariances, by the way. So the distinction about what you can and can't do is at the error level, not the factor level. Does that make sense? I'll say that again. These are factors, so they can always have widths no matter what kind of model you're in. It was the error covariances that you couldn't have in full information IRT. Okay, yeah, got it. All right. So this looks good in theory, right? This seems neat and tidy. And then you look at the loadings and you're like, no. So here's a problem. When your specific leftover factor loadings are bigger than the general ones, hard to argue that that's the leftover part just due to wording. When the specific pessimism factor loadings, most of these are non-significant. That's what the A means. I think that the 0.64 is a typo. I think it should have gone on that one, actually. So none of these are significant, and at least the factor loadings are bigger on the overall factor, but this is somewhat problematic. So if it were really just the fact that it were wording, you would not expect stronger loadings on that factor. It challenges the interpretation of what they're saying the bifactor model is. So when you're trying to fit these models, constraints are going to be essential for you to enforce the interpretation of what it is. If you have a factor that is supposed to be, positive wording, and some of the items load positively and some of them load negatively, like, it can't be positive wording then. Like, it's got to be something else. So this model is over-parameterized. It has too much stuff in it. That's what that means. So they came up with an alternative. Model number 4. They called it a random intercept factor model. It has a constraint. All of the loadings for this secondary factor are fixed to 1, despite the direction in wording. So they're saying there's an extra common covariance across all of the items, regardless of how they're measured, that is above and beyond whatever these items are supposed to be indicating the trait of optimism. And so then we're back to this pattern of some positive and some negative, meaning it is optimism and not pessimism based on the direction of the loadings. So they called this a random intercept factor because that's what it would be in like a multi-level modeling representation of this, right? The U0 that's in those things has an implicit 1 in front of it. So yeah, I'd call it a random intercept. If we were back in IRT, what would we call it then? If all the loadings are fixed equal. Fixed to 1 specifically with the variance estimated. Yeah, that's a Roche model, or a 1PL. So yeah, theta is a random intercept in a Roche model. Boom. They interpreted this as a person shift due to different response scale interpretations. That's what they called this. I have no idea if that's right, but I have used this trick a few times to capture relationships across items that would be error covariances this way. And if you can fix all of the loadings to be equal to each other, then that implies a constant source of covariance across the errors, and that can be a more parsimonious model than allowing separate loadings or separate error covariances. So something like this, for those of you who have pockets of error covariances, you could try something like this to soak it up, where this would be your new error covariance factor, essentially, and all the items that have common error covariances could load on it. Okay, how are we doing? Nodding, okay. I think a nod is a good answer for how we doing. We are doing, that is what we are doing. Questions? Does anyone want to ask, how does this apply to me, and tell me about your data? Free consulting. Well, other than the tuition dollars you paid to be here, but free-ish. Nobody feeling brave? All right, story time then. True story time. So back to the forgiveness scale. You have seen this much of it in example 4. Here's the rest of the story. So this is far and away my most cited publication. This is work that I did as a graduate student as a GRA. And I get at least 2 emails a week from people asking if they can use the scale. And I'm here to say again, internet, you may use the scale. It is publicly available. You do not need my permission. The reason that I get asked is because the lead author is no longer in academia, the second author is dead, and the third author is me. So I'm the one that gets found. But you can use the scale however you want. And it has a website and everything, and it has a number of translations into other languages. Interestingly, some evidence from those suggests a different factor structure holds in other cultures or other languages, and they usually write to us and tell us about it. And I'm like, oh, that's interesting. I don't know why, but thanks for sharing. So I don't know anything about forgiveness other than that it was somewhat contentious to measure. There's a bunch of other forgiveness measures, but nobody else addresses the concept of forgiveness of situations, which is the novel part of this particular scale. But what it is composed of is half and half positively worded items and negatively worded items that measure forgiveness of yourself, of others, and then of situations. So 18 items in total. So if we look at the total degrees of freedom and number of parameters that it would take to fit this model, we have 18 items, so it's 189 possible from the number of means, variances, and covariances across these items. I fit 48 parameters in the measurement model. So we have only 12 loadings because each of these factors has to be separately identified by having a loading fixed to 1. I do have 18 intercepts. And by the way, I should go back to these pictures here like this one. If you have a model like this that has specific factors, you may have more than 1 factor loading per item, but you still only have 1 intercept. It's only the loadings that you would have more than 1 of. So each item, like by default, starts with an intercept and a variance. And then the question is, what else do you need to add as a predictor? How many factor loadings and how many factors? So don't get that part confused. And if you're in IRT land, then you have only 1 set of thresholds, or 1 set of intercepts if you want to turn them around, or 1 set of difficulties. It's the A parameters in that case that you would have more than 1 of. And in multidimensional IRT models, they usually give up the idea of a B and just use an intercept instead, because it gets to be too ugly otherwise. Okay, structural model. So I have 6 latent factors, and I have estimated all of their variances. I have not estimated their means because I have 18 intercepts. And this set of arrows where I have a line with the arrows going in, this is my way of cheating the diagram to show all possible covariances among these 6 factors. Otherwise, that would be a lot. What is that, 15? No, more than that. How many possible covariances among 6? I can't do it in my head, but there's a formula. There's a lot, is my point, and that looks like a really super cluttered diagram if you do it that way, so I like this convention of sort of doing it. This would require a note to the reader, though, to explain what this is. So this structural model right here is saturated. This is as good as it gets. So then the question would be, is there any kind of higher order structure that we could put on it that would simplify it back to the intent? Like they wanted to have a self measure, an other measure, and a situation measure. That was what they wanted. They ended up with situation positive and situation negative, other positive, other negative, self positive, self negative. They didn't want that. But I tried many, 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 many permutations, and there was no world in which I couldn't start with the 6. The items that had the same content, intent, and the same direction just wanted to be more together. So this is the structural model that I started with. Here's what it ended up. Super funky. Okay. So this is a type of bifactor model or a method factor model, but the constraints that I put on it are different than what one would typically do, but I did it for reasons. So first off, because what they wanted to be able to talk about was self-forgiveness, other forgiveness, and situation forgiveness, I put higher order factors in which I have those variables predicting the lower order factors of the different ways of being measured. Okay, so I have higher order self that has 2 indicators, higher order other that has 2 indicators, higher order situation that has 2 indicators. Okay, so we just talked about this. If you only have 2 indicators of a factor, that's bad, right? So what I could have done to make sure that each of these factors is locally identified is fix their factor loadings within a factor to be equal to each other. So I could say that self-positive and self-negative have the same contribution in terms of the higher order factor predicting them. I chose to go a different route. I was more concerned about making sure that the impact of wording was not going to confound the assessment of the trait. So PL versus NL means positive loading versus negative loading. So I constrained all the positive loadings from the higher order factors to be the same and all the negative ones to be the same. That way the relative balance of positive to negative stayed the same regardless of what it was measuring. I don't remember which way it went, but I honestly think negative was higher. I'm not for sure about that. I'd have to go look back at the paper, and I have not read that paper in many years. Okay.
So, sorry,
Hit me.
so an equal alternative would have been to set like both of the arrows from self to 1, and then both of the arrows from other to 1.
Yeah,
Like, or not to 1, but like equal to each other.
equal to each other, yes. Yeah, so
Okay.
because I fixed these factor variances to 1, it would have to be equal to each other, but not 1. If I had
Okay.
estimated the factor variances instead, then it would have been equal to 1, which is still equal to each other.
Okay, gotcha.
Yeah. Yep. Yeah, it's just how do you want to scale it? It's an identification thing. So I chose to do it that way, and here's the code by which I would have accomplished that, so that each higher order factor had sort of the same distribution of positive versus negative. Because we think that the extent to which you forgive yourself might be related to the extent to which you forgive others, or the extent to which you forgive situations, we have 3 covariances among these factors. And if I wanted to, although I'm out of room on the slide, I could have put a higher order factor over that. Then I could have had forgiveness, and then it went down to self, other, situation, and then it went down to positive and negative, like a 3-layer cake or something. That would have made them happy. But we still have to deal with this positive, negative stuff on the other side. So I created method factors, or specific factors based on those, and I fixed all of the loadings to be equal to each other, and I also fixed the disturbance terms, the variance left over for these lower order factors, to be the same within kinds. So the same amount of disturbance if it were a positive factor, and the same amount of disturbance if it were a negative factor, to parallel what I did on the other side with the loadings. So here's my argument.
Can you repeat that?
Yep. So in the same way that I forced all the positive subfactors to have the same loadings, I forced all the positive subfactors disturbances to be the same, to have the same factor variance left over. So then I have equal amounts of like true versus error, or true versus leftover, however you want to think about it. Okay. Then with the specific factors, I fixed all of the loadings to be the same, with the logic that if it really is just this is positively worded, then it shouldn't matter which kind of positive it is. Self, other, situation, right? Because this is just a wording factor, and that's how I want to interpret it. And the same is true for the negative. Shouldn't matter which one it is. And this model fit well. And so because of all of these constraints, I saved a bunch of degrees of freedom, but then I also can maintain the interpretation that the authors wanted. They wanted to talk about self, other, and situation. They did not want to talk about method factors and wording. So then this is the like make it go away kind, where these factors over here would just sort of collect the extra covariance and we wouldn't do anything with them. Okay. Does this make sense as a choice? And all the code to do this, by the way, is over here. So I like this. I was proud of myself for finding something that fit and doing all of these constraints, right? Because I was like, you know, your age when I was doing all of this, right? This was my last year of graduate school and then into my postdoc, I think maybe a little bit. And we got the reviews back, and reviewer 3's like, no, actually, self, other, and situation are the method factors. It's 3 ways of measuring forgiveness and unforgiveness, which is what you have. Like, huh, I didn't think of it that way. So they wanted to call this forgiveness and this unforgiveness, and then I have 3 ways of measuring it based on which kind. Now, I'm not a forgiveness expert, but that seemed like a reasonable interpretation. The other co-authors were like, oh, hell no, that is not right for these reasons. I'm like, okay, but I got to answer reviewer 3. So what I did was flip the constraints. Camera 1, camera 2. 1, 2. 1, 2. So I reversed the constraints to try to enforce the alternative interpretation. So now on the left side, what I was calling positive wording, they're calling forgiveness, and what I was calling negative wording, they're calling unforgiveness. So I constrained the loadings to be the same so that the method factors had equal contributions across forgiveness and unforgiveness. So self, L had the same loading, whether it was forgiveness or unforgiveness. Other had the same loading, and then I had to go with T because I already used S. So situation, I went with T. And then I have a correlation between these two because the extent to which you demonstrate forgiveness and unforgiveness is probably going to be related. A negative correlation, as we would expect, if you didn't reverse code. If you did reverse code, then it would be a positive one. And then the method factors are over here. Now they are uncorrelated because what they have in common is just the way we ask the question about forgiveness. It's not a different kind, it's just a way to measure it. And so then I have all the loading constraints on this side to be equal, because if it's just a way to measure it, then it shouldn't matter which way it is. So in terms of degrees of freedom, they're the same. The structural model is over-identified by 13 degrees of freedom either way. So can I do like a likelihood ratio test or a diff test or anything like that if I have the same degrees of freedom? I cannot. Are these nested models? What do we think? I've got this and this to work with. No one wants to speak. Nested, thumbs up. Non-nested, thumbs down. Okay, I've got like 5 or 6 votes, all for non-nested. That is correct. So this is another example. Rarely they happen, but here's another one of a non-nested model. So we talked about this at the beginning of the semester in terms of if you're not sure which factor an item goes on, and you want to try it to like load on factor A and then move it over to factor B instead, that's a non-nested model. It would have the same degrees of freedom. So then we would have to figure out how to compare fit, not using likelihood ratio tests or diff tests. Question?
Yes, Lisa, where do you keep that box on the right corner? Self by self, post PL and L.
This?
Yes, that's the same box as in the previous slide.
Yeah, I think that's a typo.
Okay.
Yeah, thank you. I'll fix that later.
Yeah, because now
Yeah, I
you're
had the boxes.
constraining the loading to L across all the method factors, right?
Yeah, I believe that is, I need to look back to be honest, because they're inconsistent, so thank you for catching that. I'm not sure which is right.
Okay.
But I have the, these ones like this, which is over here,
Yes.
and then I would have stolen this out of my own code, so. And I'm missing a parenthesis I just saw too. Yeah, I'll have to look back. I will fix it. Thank you for
Thank you.
pointing that out. But I'm pretty sure that it's the L's that should be right because it's the inverse of what we had on the other slide. Yeah, otherwise it wouldn't have the same degrees of freedom. So I will make this fixed, thank you. I have given this slide about 10 times, and you're the first person to notice. So it's amazing to me when errors make it that far downstream. So kudos for Eagle Eye. They are not nested. So how do we compare not nested models? AIC, BIC for the win. Yep. M plus spits out two different kinds of BIC. I don't remember the difference, but I know they're in there. AIC and BIC, no matter what your software is, are always in the smaller is better direction because the root that makes them is -2 log likelihood plus some correction for the number of parameters, some kind of penalty function. So my answer to reviewer 3 was, thank you for bringing our attention to this interesting alternative perspective. We fit the model, and it fit worse, so suck it. We win. I mean, as noted in footnote 3, we compared the alternative model and reported it did fit worse. So, there you go. I would not recommend suck it in your response letter, but I do recommend it though when you first get your reviews back and you're furious with the reviewers, like to vent, get it out of your system, like I write that letter right now, and in which I get all of my feelings out, then you can be very careful not to send that one back. But that can be cathartic. So yeah, I win, because the constraints from the other direction did not support, were not as supported. So, all right. So lots and lots of examples of this in the literature. The point that I would want to drive home is use constraints to enforce your interpretation. Don't just let all the loadings be whatever they want, particularly in bifactor models that have like lots of specific factors, because then the interpretation that this is just leftover extra stuff is suspect. Particularly when it comes to wording factors, if the loadings aren't all in the same direction, that's a really bad sign that it's not a wording factor. At a minimum, they should be in the same direction, and if it were just wording, you should be able to constrain them equal and not have a decrease in fit. So this slide has a lot of crap on it, right? We can agree on that, as most of my slides do. I do that on purpose, by the way, so that you can sit and listen and not have to type so much. That's a deliberate choice on my part. But you may find yourself in the situation where you're trying to make structural model diagrams, and the model is so big that you can't figure out how to fit it on a slide or a poster or on a single page of a manuscript. So I wanted to give you a few examples of how you can cheat your diagram so that it becomes more compact and easier for folks to understand. So this is one where I had actually talked about this at the beginning of the semester for a different reason, but the part I wanted to draw your attention to is this right here. So this is cognitive control as a higher order factor with indicators of what he called easier trials and harder trials, because this is a task that is sequential. And so the first 8 trials wanted to group together, and then the next trials from 9 to 20 wanted to group together. So to draw this completely would require 20 boxes in this row, and I don't have room for that. So ... in the middle is an abbreviation. You can do this. So 1 to 8 and 9 to 20 is implied that we have all these middle loadings as well. Cognitive control, by the way, you'd have to have these 2 loadings fixed equal, given that there's only 2 indicators of this higher order factor. The other side here is, this is the punchline to the story I mentioned probably like 2 months ago or something. So this is the task where you're trying to measure teenagers' risk tolerance, risk willingness, etc. I forget the word is, where they're in a fake task where they have to drive to a party and get there as fast as they can, but then there's stoplights along the way, and so they have to decide whether they want to floor it through the intersection when it turns yellow or whether they want to stop. And traditionally, the way that people took the information out of this task was to measure the latency to hit the brake. And if they didn't hit the brake, that was considered missing data. Like, no, that is construct relevant information. If they decided to floor it through the intersection, I would call that risk acceptance. So we did this as what I would call either a 2-part model or a hurdle model, depending on what your count part is. So this is a tie-in to the generalized class, hi, and those of you who've taken it before. So I have whether or not they decided to stop or go as a binary indicator. So this part over here is like an IRT model. So I have stop go as one outcome. And then if they decided to stop, how long it took them to make that decision. So this model over here then is, since it's response time, it's going to be a continuous amount, so I would call it two-part. But if this were a count distribution of how many, then it would be considered a hurdle model instead. And it turned out that the stop-go part was the only predictor that significantly predicted this outcome of whether or not they had had sexual intercourse as an adolescent. So the decision to stop or go was related to the decision to stop or go. How's that? Never saw that coming. Come on, I get a rim shot for that, right? How long it took them to make to hit the brake did not predict this uniquely. So it turned out that if we had scored it in the way that people typically do, we would have missed the story. Here is one that I made. So this is from a multi-level structural equation model with the same research team, actually. And we have a between-person structural model, and I have a within-person structural model. So I had to show the idea of mediation in this one in particular, because the boxes on the left-hand side were considered predictors. The middle circles here, this is a growth model. So I have an intercept factor for initial levels of teacher-child conflict, and I have a factor for change in teacher-child conflict. And looked at my N dash. I even got it in the picture. N dash for compound phrases like this. Not for everything, but for this you do. And those are in turn predicting teacher-reported externalizing intercept and change, and mother-reported externalizing intercept and change. So this is a very busy diagram. I did not show any of the indicators underneath it because that would make it even busier. I tried to use patterns to help separate the lines. So the gray dashed lines are the ones that are non-significant. The significant ones are shown with the dark, with the coefficients on them, and I built this myself. Yeah, so like this picture took like a day to build. But how I did it was text boxes on the lines to put the little coefficients in. So this is the between-person model, meaning individual differences as all of the sources of variation across children. Within persons, because this is a longitudinal study, I have a separate box where I showed the relationships among the time-specific residuals for each of these things in sort of a cross-laggy, panel-y kind of flavor here. So we have the residual at the same grade predicting the residual at the next grade, prior grade, and so forth. So I didn't show any of the actual measurement models on here. I described them in the text instead because this was enough. One more. One of my students came up with this one, so I can't take credit for that, but I like this because it's a very clean way to represent a path model. And in particular, this is an actor-partner version of a path model. So that word is a type of model that is applied to dyadic data, where you're interested in how my stuff predicts my outcomes and how your stuff predicts your outcomes. Those are called actor effects, because I'm acting on myself. And then how my stuff predicts your outcomes and your stuff predicts my outcomes. Those are called partner effects, and they're always shown this way. So I'm legally required to make this gesture whenever I talk about these models. So there's a lot of stuff here. This was from a study in which they were manipulating self-control depletion. So basically making people do really annoying things for a long time until they got really tired of it, and then measuring some stuff. So we have pre-conflict negative emotion reactivity, and interaction with the manipulation, because they thought being depleted would exacerbate these problems. And so the interaction terms are shown in boxes here because that's how you would actually represent it in a path model. And instead of having 4 different arrows from these possible boxes to here and to here, she grouped them with the brackets. So we have like the actor effects labeled as A, because this is women's stuff predicting women's outcome. Then we have the actor effects for their partners. So we have the men's stuff predicting the men's outcome, and then we have the cross paths with the P labels on this, and then we have the main effect of the manipulation on both of those things. So I thought this was a really clean way to show a lot of relationships at the same time. It would be a nightmare to report the results using this diagram, but it's effective for communicating what the model looks like, I think. So all the results are in a table instead. So wrapping up then. Look, we made it to the summary slide. It's always exciting when that happens. All right, before we wrap up, any questions about the pictures? Or what is logically possible in this world of higher order structural models? Okay, then, so what I hoped to emphasize in this unit is the following. Measurement models and structural models are two different things with two different goals. The goal of the measurement model is to recreate the covariances among your items. The goal of the structural model is to recreate the covariances among your factors. You have many choices as to how you do each, but they are separate. And I have a note that a higher order factor is not the same thing as a total score. If a higher order factor model fits, it does not mean you can add the items up and call it a total and have it be fine. But it is a way to rescue a multidimensional trait that you want to think of as unidimensional. You just have to have all the stuff underneath it. So you can have a higher order factor predict stuff. Then you can think of it as if it were a total score, but you don't actually have to build the total score yourself. You can keep it in latent space. And by the way, just to put a postscript on this study, do you know what everyone does in practice with this scale? Add it up, add it up. Total forgiveness. Fine. Nope. No one on earth, I think, has ever tried to fit this model like on purpose. Just, in the original paper, that's where it is. I haven't followed the research very much, but I'm pretty sure it's most people just add it up. So I tried. But I could have a higher order factor over here if I wanted to have that. But turns out the relationships of these variables to other things depends on which kind of forgiveness you have. So a higher order factor would not be useful for articulating those things. So in practice, I recommend fitting measurement models first, separately, so that you can make sure that the items that you think are measuring the factors actually are, and that there's nothing else in common. Then you can pool the results and have a structural model with multiple latent variables at the same time. In that case, misfit has to be due to cross-factor relationships among the items that are not there. So it limits the scope of as to what can be wrong if you do it this way. And also, if you have higher order factor models that have specific or method factors, bifactor models as they are called, the loadings need to make sense. If the loadings don't make sense, then you should really rethink what you're calling your factor. And better yet, put constraints on there to actually enforce the interpretations that you want to have and to fight reviewer 3. Fight the good fight. Ta-da. Questions on any of that? Clapping, yes. It feels good to win, I gotta tell you, Which is funny because I should actually just be thankful that someone agreed to review my paper and that it didn't sit on the editor's desk for months and months and months. That's the alternative perspective. I'm an associate editor now, and that happens, right? I will sometimes have to go through like 10 people before I'll find someone who'll say yes to review something, so. Because reviewers don't get paid. The journals make a lot of money. The authors have to pay money to put their work in the journal, but nobody gets paid, just the journal. All right.